the minimal inhibitory concentration of an antibiotic X against Clostridium tetani, Staphylococcus species, Shigella species, and Streptococcus species is 25, 15, 2, and 1 mg per ml respectively. So it is given for each of these bacteria. Assuming that the bioavailable concentration of X in an animal model is 20 microgram per ml. So what is the bioavailable concentration of X is that much of an whatever antibiotic you give, that this is the concentration, that 20 mg per ml concentration uh, of the antibiotic X is seen in the animal tissues. So whenever we provide with the animal with the antibiotics, we see 20 mg per ml. If we take the tissue and we measure the antibiotic concentration in the animal tissue. So which one of these bacteria may develop resistance against X in the animal model? So this is a tricky question. So they are saying the minimal inhibitory concentration of antibiotic X against the antibiotic is same, but there are different kinds of bacteria, and these are the minimum inhibitory concentration of the different bacteria. So first we have to know what is the minimum inhibitory concentration and how we calculate it. So what we do is we prepare serial dilution of the antimicrobial agent. We prepare the test inocular. Here we have a broth, any broth we can take. Here they have taken Mueller-Hilton broth and the test bacteria. They grow the bacteria in that broth, and then we prepare different dilutions of the antimicrobial agent. So we take different antimicrobial agents, and we take we have a stock solution. From there, we prepare serial dilution. 1 is to 10 serial dilution. We take 10 raised to the power minus 1 minus 2, like that, up to 10 to the power minus 8 or minus 9, 10, whatever you can take. Each time you take 100 microliter from the stock and 900 microliter of the dissolving solution, water or ethanol, whatever may be the solution in which you dissolve the antimicrobial agent. Next, we take we then add all these into our 96 well plate accordingly. Like you have label it that 10 to the power minus 1 minus 2, like that, and then you add it to your 96 well plate. Okay, like here you add it, and then then what you do is antimicrobial agents are transferred into the 96 microtiter well plate and inoculated with the bacterial suspension. Along with the bacteria, you add the antimicrobial agent. Then what you do is you keep it for 18 hours or 24 hours at 37 degrees Celsius. Then, uh, then this is the different antibiotics you have added, or and the bacteria also, and then you have kept a sterile control, a growth control, and a test sample. So sterile control is that you do not add any bacterial inoculum, and growth control is a medium which will favor the growth. So this is the positive control, this is the negative control, and here you add all the antimicrobial agents in different dilution, and then after 24 hours, this is what you see. So you actually measure the concentration by spectrophotometer, okay, and then you determine the turbidity of the different in different solutions or different concentrations. What is the turbidity? If there is no turbidity, means the bacteria did not grow because the antimicrobial agent was very strong. It would restrict the growth of the bacteria. If there is low turbidity or high turbidity, means the bacteria could grow. Now we have to find out at what concentration the bacteria started growing. And the lowest concentration of antimicrobial agent which is capable of inhibiting bacterial growth is called the MIC. So what is that? What does that mean? So here you can see. So this is the result. White ones means there is no growth, and yellow ones means there is growth. And you can see there are different compounds A, B, C, D, E, F, G, H, and this is the compound concentration gradient. One being the highest concentration, and these are the serial dilution product. So this will be 10 to the power minus 1, minus 2, like that. Okay, and these are different antimicrobial compounds. So here you can see the growth has started from the ninth well. So and then thereafter there is growth. So MIC for compound 1, this is the compound 1, will be this concentration. Concentration at 8. Likewise, the MIC for compound 2 will be the well before, from where the growth has started. Like just the previous well from where the growth has started. Not the well from where the growth starts, but the previous one. The previous one. For 2 and 3, they have the same MIC. For 4, the MIC is well number 6. Likewise, there are different MICs. So, we now come back to the question. So here what they are saying, from Clostridium tetani it is 25, Staphylococcus 15, Shigella 2, and Streptococcus 1, and minimum inhibitory concentration for different bacteria, and bioavailable concentration of X is 20. So in the tissue, the concentration of X will be 20. So 20 is higher than 1, 2, and 15. So for bacteria Streptococcus, Shigella, and Staphylococcus, the concentration of X is higher than their minimum inhibitory concentration. So therefore, they will be, so because the concentration is higher, the bacteria cannot grow in that concentration of antibiotics. So these bacteria would not be able to grow because they are 15, 2, and 1, that is Staphylococcus, Shigella, and Streptococcus cannot grow. But Clostridium tetani needs an MIC of 25. But here the bioavailable concentration is 20. Since its MIC is higher than the bioavailable concentration, the bacteria will, uh, like, there will be some resistance in the growth. Okay, but it may overcome that resistance in due time because its MIC is higher than the bioavailable concentration, and it will likely develop a resistance against X, and so it will grow, albeit lower growth rate will be very lower, but slowly and steadily it will start developing a resistance against X, and in the later generations it may happen that its MIC will also get increased because of continued growth in that antimicrobial agent. It may develop a resistance against X. So the answer here will be A, Clostridium tetani.